All right, time for some stoichiometry. And so just a reminder about balancing equations. So with this one here, if we're going to try and get the nitrogens to match in 2, we're going to put a 2 in front of here. And now we have 6 of K. So we're going to put a 6 over here. And then with that 1, this is going to be a balanced equation. This is creating a mole ratio. These numbers are going to be really important with stoichiometry. And so here we're going to use it to find how many moles of K3N can be made from 12 moles of K. So we're starting with that 12.5, not 12, mole. Okay. And now we do that dimensional analysis thing. So you match up the 6 moles of K from that equation that we had before to the K3N, which had that coefficient of 2. So that's 2 mole K3N. So that multiplied out is just 4.17 mole K3N. And just a reminder that we have 3 sig figs here because 1, 2, 3 right there. Example 2. How many moles of N2 react with 0.425 moles of K? So we're using that same equation from earlier. So we have a 6-to-1 K to N ratio, or K to N2. And so here we're starting 0.425 moles of K. Then we're matching that up. Moles of K on the bottom so that they cancel out. Moles of N2 on the top. And then you just multiply that out. 0.0708 because we have 3 sig figs. Moles of N2. How many moles of N2 are needed to react with 64.4 grams of K? So now we have an extra step because we're trying to get grams to moles. And so we start off with that 64.4 grams. Okay. And now we need to reference the periodic table to know that in 1 mole of K, there are 39.10 grams. And now we do that same for every 6 moles. Okay, there's 1 mole of N2. And now, when everything cancels out, we are in the correct unit. So that multiplied out is going to be 0.275 moles of N2. How many grams of N2 are needed to make 1.254 moles of K3N? So, very similar process. Start with what's given, 1.254 mole K3N. Now we get to match moles to moles again. 2 moles K3N. 1 mole N2. And now we go from moles to grams. So in every mole of N2, according to the periodic table, that's going to be double of what nitrogen is. So that's going to be 28.02 grams of N2, which is equal to 17.57, because there's 4 sig figs, grams of N2. And so let's just use a different reaction here. To balance this out, that's going to be 1 ZnBr2, 2 AgNO3, 1 ZnNO3, 2, and then 2 HBr. And again, this is going to be our mole ratio, 1 to 2 to 1 to 2, that we're using in our stoichiometry. So fifth example, how many grams of ZnBr2 are needed to react fully with 45 grams of AgNO3? So we start with that 45 grams of AgNO3. And so we have to go through the mole ratio on this one that we get from this equation before we can convert to grams. So we're going to have to go from grams to moles to grams again. And so now we also need to calculate, because it's not just a straight up element, this is a molecule, compound. From 1 mole AgNO3, when you calculate that out separately, you get 169.88 grams of AgNO3. And now we get to use that mole ratio. 2 moles of AgNO3 per 1 mole ZnBr2. And now we convert back to grams. Mole ZnBr2. There's 225.19. Again, calculated separately. ZnBr2, which equals 30 point, because there's 2 suffix there, 30 point grams ZnBr2. And then our last example. How many grams of AgBr2 are produced when 10.25 grams of ZnBr2 reacts? So again, we're going to have to go from grams to moles to grams. And so 10.25 grams ZnBr2. Calculated earlier. Up here, how many grams in a mole? So let's use that again. 225.19 grams ZnBr2 in every mole. And then that mole ratio again. 1 mole ZnBr2 for every 2 moles of AgBr. And now we convert back to grams. So in 1 mole of AgBr, we haven't used this one yet, so you calculate on the side that is 187.77 grams of AgBr. And so that's 1709 4 sig figs AgBr, and that's grams.